So now let us look at the topic graph of a relation versus graph of a function, and more specifically VLT, that is the vertical line test. Let us see what this is. So now let us take a relation between x and y. So some relation between the sets A and B. So we know that relation from A to B is some way of mapping some elements of set A to some elements of set B, right? So let us take a definition. So let us take y square is equal to x. So this is some relation between A and B. Let us take A as real numbers and B as real numbers. That means if you draw the diagrammatic form of this relation from real numbers to real numbers. So obviously when if a relation is defined from real numbers to real numbers, expressing it in diagrammatic form looks clumsy because real number set is not a discrete set. It's a continuous set. That is, the numbers grow continuously. I cannot write it like this because between 0 and -1 you have infinite number of real numbers, and between 0 and 1, 1 and 2 you have a lot of real numbers. So it's not a good way of representing a relation when the relation is defined between continuous sets. So for example, let us try to do it, right? So this is a set of real numbers to real numbers. You have a lot of numbers between 0 and 1 also, which I'm not writing. So now what is the definition of this relation? Y square has to be equal to x. That is, if x is equal to, if y is equal to 1, if y is equal to 1, x is equal to 1. If y is equal to -1 also, x is equal to 1, right? So that means if x is equal to 1, y can be equal to +1 or -1. So in both cases, if you do y square, y is the element in the second set. -1 whole square is also equal to 1. 1 whole square is also equal to 1. And 0 is related to 0. So -1, can y square be equal to -1? No. That means -1 does not have an image. All negative numbers don't have an image. Next, if you take 2, 2 will be mapped to, if x is equal to 2, y has to be equal to plus or minus root 2. So plus root 2 minus root 2, they'll be somewhere in this real number set. So 2 will be related to plus 2 and minus root 2. Similarly, 3 will be related to plus root 3 and minus root 3. 4 will be related to plus 2 and minus 2, so on. So if you want to draw the graph of this, so whenever you want to draw the graph of a relation between continuous functions, so diagrammatic form is not the good way. So we just draw a table. So remember, this is a standard process in which you draw graphs of relations. So x and y. So you take some sample points of x and y which satisfy this relation. So if x is equal to 0, y is equal to 0. If x is equal to 1, y is equal to +1 or -1, right? If x is equal to 4, y can be equal to +2 or -2, so on. If x is equal to 9, y can be +3 or -3, so on. This is how the points go on. And we plot these points on the graph. So the first point is 0, 0. That means this point is there on the graph. 1, 1 means this point is present on the graph. 1, -1 is also present on the graph. Next, 2, 3, 4. So 4, +2 lies on this graph. 4, -2 also lie on this graph. So on. These are the sample points. And in between these points, you also have some points. But you don't need to plot all the points. You take some sample points on this graph and then join them with a smooth line, smooth curve. So this gives you the graph of the relation y square is equal to x. So this is the graph of this relation. Now every relation or every function for that matter has some sort of graphical representation. Now if you want to check whether this graph represents a function or not. So we know that a function is a relation which satisfies certain conditions. What are the conditions? Every element in the domain should have one and only one image in the codomain, right? So now let us check whether this relation, this graph satisfies the conditions. So first condition, every element in the domain has to have an image. So to check that, I'll draw. So now let us look at another relation between real numbers to real numbers. So let us take a relation R defined from real numbers to real numbers, and this time let the definition be y is equal to x square. Previously the definition is y square is equal to x. Now the definition is y is equal to x square. So how does the graph of this look like? Again, whenever you have to draw a graph of any particular relation, you just draw a table first. Draw a sample table where you get different values for x and y. Now if x is equal to 0, x square is equal to 0. If x is equal to plus 1 or minus 1, y is equal to 1. That is 1. If x is 1, y is 1. If x is minus 1 whole square is also equal to 1. Next, if x is equal to 2 or minus 2, x square will be equal to 4, right? So these are some sample points on this curve. So first let us plot them. So the first point is 0, 0. That means the graph has to pass through this point. And next, the graph has to pass through the point 1, 1. And the graph has to pass through the point minus 1, 1. This time minus 1, 1 is here. And next, when x is equal to 2, y is 4, 2, 3, 4. So 2, 4, the graph has to pass through this point. Minus 2, 4, the graph has to pass through this point. So now once you have sample points on the graph, just need to join them with a smooth curve to get the graph of this function, graph of this relation. So I'll just join them. So this is how the graph looks like. So we have seen the graph of y is equal to x square and x square, y square is equal to x. So now let us see what VLT is all about. So now we have seen the graphs of two relations. Y square is equal to x. This is the graph that we have got. And y is equal to x square. This is how you got the graph of this. So from these two graphs, can you decide which of this graph represents a function and which of this graph does not represent a function? So you know that both of these are relations between real numbers to real numbers. And a relation is a function if it satisfies the condition that every element in the domain should have one and only one image. So this is the condition that if a relation satisfies, then it becomes a function. So now let us see whether this relation satisfies this condition or not. Now what is the domain? So domain is real numbers, that is encompassing from minus infinity to plus infinity. So now let us take a number in the domain which is minus 1. So let us take x is equal to minus 1. And correspond to x is equal to minus 1, do you have the image for this element? That is, if you take the diagrammatic form, correspond to x is equal to minus 1 in the real numbers, do you have an image for this? So as you can see, correspond to x is equal to minus 1, you don't have any point that lies on the relation. That means you don't have any y correspond to minus 1. That means minus 1 does not have an image. So if you draw a vertical line at the point x is equal to -1, you can see that there is no point in the curve, on the curve, which lies on this vertical line. That means corresponding to x is equal to -1, there is no y. That means -1 is not connected. One of the condition has been contradicted. That is, not every element in the first set has an image. So this is not a function. And also, let us go to x is equal to 1. So corresponding to x is equal to 1, if you draw a vertical line, it cuts the curve at 2 points, right? At 2 points. That means corresponding to x is equal to 1, y is equal to 1 is also satisfied by this equation. Y is equal to -1 is also being satisfied. That means corresponding to x is equal to 1, you have two images, 1 and -1. So which again contradicts the definition of a function. So if a relation has to be a function, every element should have an image, and you should have one and only one image. You should not get more than one images. So here two conditions of the function are being contradicted, hence this is not a function. Because some elements in the domain don't have a image and some elements in the domain has multiple images. So even if you take x is equal to 2, if you draw a vertical line, it cuts the curve at 2 points, right? That means for x is equal to 2, you have two images, which is not the case if this has to be a function. So I can conclude that this is not a graph of a function. This is just a relation between x and y, between r and r. Now let us go for this function, this relation. Y is equal to x square. Now the domain of this relation is R, and the range of this and the codomain of this relation is R. Now let us take any element in the domain. Let us take -1 or -2 or -3, so on, whatever the element is. Now let us draw a vertical line at this point on the domain. So as you can very clearly see, this vertical line meets the curve at only one point. Because this curve continues to infinity, even if I draw a vertical line corresponding to x is equal to 2, it will cut the curve at some point corresponding to x is equal to -3, because this curve goes on. If I draw a vertical line corresponding to x is equal to -3 also, it cuts the curve at exactly 1 point. Corresponding to x is equal to 0, the vertical line cuts the curve at 1 point. Corresponding to x is equal to 1, it cuts at 1 point. At any point on the domain, if you draw a vertical line, you can see that the vertical line cuts the curve at exactly 1 point. What is the meaning of it? Corresponding to every x in the domain, you have one and only one image in the codomain, which is the definition of a function. That means this graph is satisfying both the conditions of a function. Wherever I draw a vertical line, I am getting one image. Wherever I draw a vertical line, I am getting only one image. Hence, this is a function. So I hope you have understood what vertical line test is. So vertical line test says that, so if you take a graph, and if the graph is a relation defined in a particular domain and a particular codomain, at any point on the domain, if you draw a vertical line, it has to cut the graph at exactly 1 point. Not less than 1, not more than 1. If the graph satisfies that condition, then the graph will be a function. So now let us write this down properly. So the vertical line test says that a vertical line drawn at any point on the domain, which is on x-axis, should cut the graph at exactly 1 point. So if this condition is satisfied, then the relation will become a function. So let us look at some examples. So first let us take a relation defined between -1 and +1. So let us say that the domain of the relation is just between -1 and +1. And between -1 and +1, does this represent a graph of a function? So the answer is no, because So between -1 and +1, take any point and draw a vertical line. So as you can see, this vertical line is cutting the graph at more than 1 point. That means correspond to this x, there are 2 y's. That means this x is being related to more than 1 y's. That means this is not a function. So because if it has to be a function, every x should have one and only one image. So here, because this function is defined between -1 and +1, you don't need to draw the vertical line outside the domain. So the vertical line test should be done within the domain. So within the domain, so whatever vertical lines you draw, they are cutting the curve at more than 1 point. Hence, this is not a function. Next, if you take this function, assume that this is a graph defined on the set of real numbers. That is, the domain is all real numbers. And this graph is going on indefinitely. So if you draw the vertical lines at any point on the domain, you can clearly see that they are cutting the graph at one and only 1 point. So this is the graph of a function. So let us say that this graph is being defined on real numbers, that is from -infinity to +infinity. Then you need to check VLT at every point on the domain. That is, if you draw a vertical line at somewhere at this point, you can see that this vertical line is not cutting the graph. That means this x does not have an image. And if you draw the vertical line here, this x corresponds to 2 images. So some points have more than one image, some points do not have an image, and this is not a function. So if you take this graph, so this wave is going on indefinitely. That's what this arrow says. If this wave is going on indefinitely, if this relation is defined on the set of real numbers. So as you can very clearly see, wherever you draw a vertical line, the vertical line is cutting the graph at one and only 1 point. Hence, this is a function. Now let us take this graph. So let us take two cases. If this graph is defined on the set of all real numbers, if this graph is defined on the set of all real numbers, so then this will not be a function, because for negative real numbers, you can see that you don't have an image. For positive real numbers, you can see that any vertical line is cutting the graph at one and only 1 point. So if this graph is defined on all real numbers, this is not a function. But if this graph is defined only on the positive real numbers, that means you need to do vertical line test only on the positive side of x-axis. And on the positive side of x-axis, VLT is getting satisfied. Hence, on R plus, this is a function. On real numbers, this is not a function. So I hope you have understood what the importance of domain is. So some relations, some graphs might be functions on a particular domain, not on the complete set of real numbers. So if you take this, so let us say that this is a relation defined on just this set 1, 2, 3, 4. This is a discrete domain. Assume that this is a relation defined on discrete domain. That is, the domain is only 1, 2, 3, and 4. Now VLT has to be applied also at just 4 points. That is the point on the domain. So you have 0. This is 1 point on the domain. You draw a vertical line. So you got exactly 1 point on this line. Correspond to x is equal to 1 on this vertical line also, you got exactly 1 point. Correspond to x is equal to 0, 1, 2, 3. Let us say that this function is defined on 0, 1, 2, and 3. So correspond to x is equal to 2 also, you have only 1 point. Correspond to x is equal to 3 also, you have 1 and only 1 point. So every point on the domain, the vertical line drawn has 1 point of intersection. 1 and only 1 point of intersection. Hence, this can be called a function on the domain set 0, 1, 2, and 3. So I hope you have understood the concept of the vertical line test. Thank you.